Good evening, students. Today we're doing 915. It's triple integrals. So today it's the beginning of what we call triple integrals and how it makes actually finding the volume of a solid is much easier. So let's start with this integration. How would you integrate something like that? It's just a trend here. Remember, this is now we have triple integration, double. This is the first two, and this is the first one, 1 to 3. And it says dz dy dx. So I'm now integrating with respect to three variables. Same thing as two variables, but now we're going to do it with the three variables. So how do we start? We start actually from the inside. Usually we start from the inside. So what do we say this is equal to? Integration from 1 to 3. Integration from 1 to x. Now, what's the integration of 24 xy with respect to z? Now, all of the 24 and x and y are constants. Now, so what do we integrate? We integrate the dz. The derivative of dz is z, and this is from 2 to xy. Got it? This is the inner. And then what do we say? dy dx, which is equal to integration from 1 to 3, integration 1 to x. Now, we are going to replace, don't forget, we integrated with respect to z. So our star here is the z. So be careful, and you have to know what are you integrating for. I'm integrating for z. So what do we do in this case? We are going to replace z with xy, then replace z with what? With 2. So that means it's 24 xy. I'm going to replace z with xy, then minus 24 xy. We replace z with 2. We close, and we say this is dy dx. Simplify this, you will get the integration from 1 to 3, integration from 1 to x. This one is definitely 24 x squared y squared minus 48 xy, and then we say dy dx. Now, where do we go to? We go to the inner one again. So now I'm going to go inside. We integrate all of this with respect to y. So this is equal to the integration from 1 to 3. What's the integration? This is all constants, guys. So this is 24 x squared. The integration of y squared is y cubed over 3 minus 48 x. The integration of y is y squared over 2. And this is from 1 to x. And we say dx. We put this again still in a box. And this is equal to the integration from 1 to 3. Now, this one with 24 is 8. And now what we're going to do, we don't forget that our star now is the y. So our star is actually the y. And this y. So we're going to replace this y with x, and then this y also with x. Then we replace it with 1, and here with 1. So this is equal to, this one actually we said is 8. So this is 8x squared. Now I'm going to replace y with x. So this is x cubed minus 40. Oops. Minus, now this one with this one is actually 24. So this is 24. Better to simplify it. 24. Now x. Now we're going to replace y with x. So this is x squared minus open bracket. Let's replace y with 1. So this is 8x squared. Then 1 cube is 1 minus we said this is 24 minus 24. Replace x stays x and replace y with 1. 1 square is 1. That's it. We close and we say now dx. And this is equal to the integration from 1 to 3 of 8x to the 5 minus 24x cubed. This is x cubed. This one here is minus 8x squared, and the last one is 24x dx. Perfect. Now where do we go? Go to the last integration with respect to x. Now this is equal. Now with respect to x. Here is with respect to x. So now this is equal to 8x 6 over 6 minus 24x to the 4 over 4, right? It is the integration of this one. This is minus 8x cubed over 3 plus 24x squared over 2. And this is all from 1 to 3. Now this one with this one is 4 over 3. So this is 4 over 3 x to the 6 minus 6x to the 4, because this one with this one is 6, minus 8 over 3 x cubed plus 12x squared, and this is from 1 to 3. Now we put the 3, so this is 4 over 3, then 3 to the power of 6, minus 6, 3 to the power of 4, minus 8 over 3, 3 cubed, plus 12, 3 square, minus. We put 4 over 3 times 1, minus with minus becomes plus 6, plus 8 over 3, minus 12. You simplify all of this, and you should get 517 and a third. That's the answer. Okay. It's a big number, so you don't have time to simplify it. You can always use your algebra and simplify this expression. All right, now. So what happened is, now, I don't know how this one came here. So let's stop this for a minute, please. So I can clean it. All right, there you are. All right. Now, how do we integrate a function in three-dimensional space? I mean, I have now a surface, okay? What happens when I integrate a function, f of x, y, z, over triple integration? So what happens here? We don't say dA, what do we say now? dV over d. So now I'm going to integrate with respect to 3 dimensions, x, y, and z. When we talk about 3 dimensions, that means we're talking about the surface. So the surface has a dimension d, 3-dimensional region. So d is the region. R is 2-dimensional region. D is a 3-dimensional region. Okay, now how do we integrate this one? It's up to you now. You can put it dz, dy, dx. You can put it dx, dy, dz. The order now is up to you. You decide the order that is really convenient for you to integrate. Where z is what? Look at this one now. Here's a 3-dimensional, the graph here. This is actually z, the top of the solid. Here's my solid, by the way. This is our solid. This is the top, and there's the bottom. So imagine that you are standing here at the bottom, and you're looking up. When you go up, what's going to happen? You're going to cross that surface from the bottom, right? Or let's say from here. You're going to come in, and you're going to see the first lower surface of your surface, the lower part of your surface, like you're looking at the bottom of the car, or at the bottom of the plane. The bottom of the plane, the curve of the bottom definitely is different from the top of the plane, isn't it? The bottom of the car is straight. The top of the car is curved. So what's going to happen? You are going for Z, to put the bottom part, here it is, first, and then on the top, you put the top one. So now you're going to go pass through, so you get into the plane from inside, from the bottom, and then you go from the top. When you go from the bottom, look at what curve you passed. When you go from the top, look at what's the new curve that you passed to get out of that plane of the surface. Clear? So it's like, imagine a bullet comes into that thing, so it hits from the bottom. What's the curve that it hits? And then when it went out through, what was the curve that it went through? Now, with respect to dy and dx, this could be dy dx, could be dx dy, depends on the region, right? Remember, there are type 1 or type 2. So what's happening? You look at this one. Let's imagine this shape, this actually solid, and there's the sun above it directly. So the projection of the shadow is going to be what you see here on the floor. This is the shadow of the surface, like the shadow of, like the plane, if the sun is directly above it, so the shadow will be what? On the ground, and this is our shadow. Now, this shadow can be considered as region of type 1 or type 2, and you make your decision and you integrate. So the major thing in this one, in three-dimensional integral, guys, is basically your surface. What's the bottom? What's the top? The bottom is Z1 and the top is Z2, or F1 of XY and F2 of XY. Now, the projection of the solid or the surface on the ground on the XY plane could be a region of type 1 to region of type 2, and we already did this one before. And by the way, it could be even what? Polar, right? So it's up to you. You decide what you need to do with it. Now, the neat thing in this one, if this is 1, so you see, if I took it to be 1, what's left? I'm just integrating dv with respect to d. So look, what is this? You know, all the integrals are going to cancel the derivative. So what do we have? We have the volume of what? Of that three-dimensional space. That dimensional, sorry, surface. So what happens is that if the f function here is 1, then you are actually finding nothing but the volume of what? That dimensional surface. And this is, guys, how you do triple integration in finding the volume of a solid if the f function is 1. Let's take an example here. Show that the volume of a cube of side A is a cube. Okay, let me show you the graph here. We have a three-dimensional space. This is Y, this is X, and this is Z. So of side A, so on the x-axis, let's go A here on the x-axis, and A on the y-axis, and A on the z-axis. So let me make the cube that we are looking for. There you are. So this is the front. Definitely you can see all of this. And this can be seen. This is the front here also. This is something we can all see. So this is, guys, our cube where each side is A. So this is A, this is A, this is A, this is A. All of them have length A. We know that the volume is height times length, width of height, right? Length times width. Sorry. Length times width times height, which is A times A times A. This is the length. This is, for example, the width, and this is the height. And you get what? You get a cube. Let's prove this one using triple integral, guys. Triple integral says the volume is the triple integration of dv over the d. D is this space that you see here. This surface, the box that you see, the cube that you see here. Alrighty, now, so what do we do now, guys? Imagine yourself now going from here, from the bottom, you're looking from down. You're going to go look up. So you're going to go through the box from the bottom, guys. So now you went through from the bottom here. Now you went through. So what is this, by the way? If you ask yourself, so I'm going to start with saying this is equal to first two integration, or actually let's make the first two black. And the third one is dz. If you look at the bottom, you go through the box from the bottom, guys, you're going to pass through this point, and this is on the xy plane, right? We are here in what? In the xy plane. In the xy plane, we know that z is what? Is 0, right? When you're on the xy plane, z is nothing but 0. So from here, z is equal to 0. Then you're going to go through the box inside, and then here somewhere, you're going to go out. When you go out, you're going to go through this, right? This is z equal to what? If you look carefully, this is z equal to a, isn't it? You are here. This is the plane, z equal to a. So you're going to start from z equal to 0 to z equal to a. This is from the bottom to the top. And then what do we write now? We write the other values of, dy, for example, dx. Let me put it dy dx. Now, I finished the z. Let's look at the base now. Where is the base? This is our base r. I will take it here in the xy plane. And we on the x, it's a, and on the y, it's a. So you see this xy plane, this base here. This is the base on the xy plane. I'm taking it, here it is. Since I put dy over dx, so I'm going to consider that this is a region of type 1. So I'm going to take a vertical light. You see, the scan will start from here, and it will start moving. Okay, when we start from here, guys, x is what? This is x equal to 0. Up to what? This is x equal to, as you see, this is a, so x equal to a. So for x, it's from 0 to a. Now, this light of the scanner, to scan this square, starts from where? Starts from here. What is this? This is y equal 0. So we start from 0 for the y, up to this line. So the length is from here to here. This one is y equal to 0. And here, if you are here, as long as you are on this line, this is y equal to a, isn't it? So this is up to a. Got it? So I took the base, guys. This is our base. I took this base and I grafted here. And I considered it as a region of type 1, and I made my work. Now, what do we integrate with? We start from inside. What is this equal to? The integration from 0 to a. The second integration from 0 to a. What's the integration of dz? It's z. From where? From 0 to a, then dy dx. Now we plug the a, then the 0. So this is equal to the integration from 0 to a. Integration from 0 to a. Now we replace with z with a first, minus what? 0. dy dx, which is equal to the integration 0 to a, 0 to a of a dy dx. Now, where do we go to? We go to the inside again. So what do we get? Integration from 0 to a. What's the integration of dy? You know, a is constant. So what's the integration of dy is y. So the answer is ay from 0 to a. And this is what? Dx. What do? We say this is 0 to a. Now we replace y with a. So a times a is a square minus we replace y with 0, you get 0 dx. So we are left now with the integration from 0 to a of a square dx. Again, a is a constant. So this is what? This is, and okay, so sorry about that. So a square stays, and the integration of dx is x from 0 to a. What do we do? We plot a first, so here is a, minus we plot the 0. A first, then the 0. And the answer, guys, is a cube. And this is how we use triple integral to find. So what did we do here, guys? We looked at the solid. First, we started with dz. Okay, since I'm starting with dz, then my integration has to go from the bottom to the top. From the bottom, this is z equal to 0. The top is z equal to a. So those are the limits. And then I took my region, the base, and I put it as a type 1 region, and I finished the integration. Let's go to more solid functions. What is the volume of the solid in the first octant bounded by z equal 1 minus y square and y equal 2x and x equal to 3? So first, let me graph that thing here. All right, let's put the graph first. We're going to start, guys, with z equal 1 minus y square. This is nothing but y square minus y square, and it's what? It is shifted 1 unit up, right? And it goes down. So it's the graph looks like this. It's go to 1 and make the 1 minus y square. This is the graph of it. And if z is equal to 0, so this is 1 on the y-axis. And this is 1 on the y-axis also. So this is our y-axis. All right? So, but in this one, we know that x is what? In that graph, we know that x is free, right? X here. So here we're going to say x is a free. So what's going to happen to this shape, guys? It's going to move on the x-axis up to x equal to what? To 3. You see this x equal to 3? Let's put 3 here. And make x-axis, y-axis, same thing, z-axis here. Here's the z-axis. This is the y-axis. And this is the x-axis. What I'm going to do, I'm going to go again to 1 and make the same graph, guys. And connect those here. And how does the connection look like? So this is what we have here. So probably we can go like this. And in the back, we can join those in the back. And this is how it looks like, guys. Okay, so it's like a tent or something. Alrighty, so this is our shape. So let me remove some of those unclear ones. Okay, there you are. So this is our solid, guys. Now, what do we know about this? Who's going to come now? Y equal to 2x. Here's the y-axis, and here's the x-axis. Y equal to x is something like this, right? So this is y equal to x. This is the graph of y equal to x. What's y equal to? You know, here z is free. So this is going to go up and down. So it's like a plane, huh? It's a plane that's going to come and cut this. So what is the result of the cut? Let me put the color again, black. So the graph is going to go like this. Oh, man. And it's going to come like this. So from all of that, what do I need? I need to cut with this line. So this is actually the region that we're talking about, only that part. Okay, so if I graph it again, Here it is. This is 1. You go also to 1 here on the z-axis. Then you go parallel to the x-axis and you make your next line. And this is y equal to x. And this is my region that I'm talking about. Okay, so this is the solid. I need to find its volume. All right, so let's do it. All right, guys. Now, how do we integrate this one? Where is the top? Where is the bottom? And etc. So this is your solid. So imagine yourself from the bottom coming here, and you're gonna go through the base. This is the base, right? This is our base. So let me change the color for the base. Here is our base. Where is this space? This space is in the XY plane, correct? This is our base. If you look at this space, where is it? Here, we know that Z is equal to what? 0. Now you are in the XY plane, right? Now, when you go through this body here, you're gonna come out from here and this is the exit. So here is the point on the surface outside. But this is what? This is Z who? Isn't this the graph of this function? It's our what? Dome, huh? So this is 1 minus y squared. This is the top. So what would I do here? I would say that the volume is equal to triple integration. I'm going to start with dz, which starts from 0 to 1 minus y squared. From the bottom is z equal to 0 to the top 1 minus y squared. Now, let's take our base. This is our base, guys. This one, don't forget, this is y equal to x. If I take this one on the xy plane, okay, if I take this one in the xy plane, what do we get from this one? Y equal to x, here it is. And here we know that this one is y equal 1, isn't it? Here is y equal 1. This is y equal 1. All right. Now, what do we have? This one is y equal to x. We can consider this as a region of type 1. So I'm going to put with different color, double like this one. A scanner will start from here. So I'm going to write now dy dx, where on the x-axis we start when x equals 0. Now the scanner is going to keep on moving and it will stop here. What is this on the x-axis? We know that here this y equal to x, and we know that y is 1. So let's find what is this on the x-axis. So y equal to x, but I know here y is 1, so 1 is equal to x, so x is equal to half. So that means this is half. So we're going to go for the x from 0 to half. Okay, this is from left to right. Now, for the y from the bottom, who's this y at the bottom? Y equal to x, so this one 2x at the bottom. Up to the top, what's the length on the top here? As long as you hear y is equal to 1, so this is equal to 1. And this is, guys, how you find the boundaries. First, the bottom of the solid, the top of the solid. The bottom is z equal to 0. The top is my surface itself, z equal 1 minus y squared. And then I looked at the down. I found that I have this triangle. I graphed it on the xy plane. This one is the xy plane. We know here y is equal to 1 fixed because it's parallel to the x-axis. And we know that this is y equal to x. Here it is. And then I have this triangle and I set up my integral. All right, guys. So this is the finishing of this integral. Now, what do? We can integrate this one. By using the z first. So this is equal to integration from 0 to half x integration from 2x to 1y, and then the integration of dz is z from 0 to 1 minus y squared. Then we say dy dx. Now what do? We replace z with 1 minus y squared. So this is the integration from 0 to half, integration from 2x to 1. Put 1 minus y squared, you get 1 minus y squared. Then you say minus 0. We don't have to put the 0. All of this dy dx. Now what do? We integrate with respect to y. What is this equal to? It's the integration from 0 to half. The integration of 1 minus y squared. The integration of 1 is y. The integration of y squared is y cubed over 3. And this is from 2x to 1. And we say now dx. All right, so now I'm going to take you down a little bit. Now this is equal to integration from 0 to half. Put the 1, you get 1 minus 1/3 minus, now put the 2x, you get 2x minus 8x cubed over 3. And all of that dx, which is equal to integration from 0 to half. 1 minus 1/3 is 2/3 minus 2x, if I open the bracket, minus 2x, then plus 8 over 3 x cubed dx. Now we integrate with respect to x, guys. What's the integration of 2/3? So this is equal to 2/3 x minus, the integration of x is x squared over 2, so the 2 goes away. This is x4 over 4. 4 with 8 is 2, so this is plus 2x4 over 3. And this is from 0 to half. What do we do now? We plug the half. So it's 2/3 times half minus, put 1/2, so this is 1/4, plus 2 over 3. If I put half, I will get 1 over 16. This 2 goes with this one, and you got 1/3 minus 1/4. Then this one with this one is 8, so plus 1 over 24. The least common with those is 24. 24 divided by 3 is 8, minus 24 divided by 4 is 6, plus 1. And all of that is going to give me 8 minus 6 is 2 plus 1 is a 3 out of 24, which is equal to 1 out of 8. This is exactly the volume of this small solid. If you need the other side, you can also do it. So I thought that he wants that piece. So I use my work to find the solid of this small piece. In the solution, I'm using the other side. You could do it as the same thing here by going to the other side if you like, but I chose here the small one. All right, let's look at this one. Evaluate this one where D is, now we don't want to find the volume actually. This is not a volume uniform because inside we have this. But over what? Over the three-dimensional surface that has the graphs of y equal x squared, z equal 4 minus y, and z equal to 0. Where is that shape exactly? Let's see where we are here. So let's start with the line. We have y equal x squared. It's going to move on the function up and down. Okay. And z is equal to 4 minus y. Well, what is this? So we have so many regions to think of. Okay, so let's start the work. All right. So y equal to x squared is exactly that graph. Right? This is actually y equal x squared, because this is the y-axis, and this is the x-axis, and that is the z-axis. Now, this is going to move what, guys? Up onto the z-axis. It's going to go up and down. Before I take it up and down, so you know this in this equation, z is free. So this curve is going to go up here. So let me see if I can take a copy of this. Here it is. And if you notice here, you will notice that what do you have? The result is going to be something like this folded paper. You know, this is the three-dimensional thing that you see. When y equal x squared moves up and down, this is the result. It's going to be that dome, but it's facing the right. All right. Now, who's going to come now? Z is equal 4 minus y. How do we graph this one? We let z equal to 0, guys. So that means y is 4. Where is 4? Let's put the 4 here. When y is 0, z is 4. Let's suppose that 4 is here, guys. So it's a line, right? This is supposed to be a line. But actually, this is not a line. What is this? This is a plane. Here, the x is a free, right? In that one, x is a free. So this line is going to go right and left. When it goes right and left, what's going to happen? It's going to cut that shape. So the result is going to be something like this. And I would suppose it's going to look like that. See that? So this is our shape. All right, so let me put it here. This is our curve, y equal x squared. Then here at y equal to 4, this is z equal to 4 also. So what's going to happen? We will have something like this and something like that. See the shape? This is the shape that I'm talking about. This is our shape. It's a cut. We cut that folded paper. We cut it with y equal x squared. This might be too deep. So let me make a minor fix here. This could be too deep. So we can do it a little bit accurate. Okay, how about that? I should be proud of myself that I'm able at least to make three-dimensional graphs. This is the y-axis, and this is the x-axis. So this is our solid, guys. So now this solid is standing on the ground. Why? Because it says z equal to 0. Z equal to 0 is what? It's the xy plane. So this shape is not going to go all the way down. It's going to stop at z equal to 0. Where is z equal to 0? This base here is our z equal to 0. This one here, z equal to 0, because it's on the ground. So when you look from the bottom, what do you see at the bottom of this shape? It's z equal to 0. So the value, so this is the triple integration of x squared plus y squared. We are going to start with dz, guys. Z is from 0. Now, where is this other surface when you go through? This is the through surface, right? This is the through. So you're going to go from here. But this is the graph of what? This is the graph. Who's this cut? This is straight cut is what? This is z equal to 4 minus y, isn't it? That's not y equal x squared. Y equal x is on the ground. Who's the top? Z always equal to 4 minus y. So up to 4 minus y. Now, let's look at the base. The base now is like this. It's y equal x squared up to y equal to 4, isn't it? See, it's up to y equal to 4. This is y equal to 4. This line is our y equal to 4. Here it is. And this is y equal x squared. All right, where do these two curves meet at on the x-axis? What is this point and what is this point on the x-axis? You know, when you say y equal x squared and y equal to 4, this is the intersection between these two lines. So this implies that x squared is equal to 4. So x is equal plus minus 2. So this is 2 and this is 2, negative 2. Now what do we do? I can consider this as a region of type 1. So I'm going to start from here. So the scanner, guys, is going to start from here, which is what? From negative 2. So I'm going to say dy dx as a region of type 1. And the scanner is going to start from here and it's going to move. Keep on moving till what? Where does it stop at? It's going to stop here. So now I cover the whole region. Where did it stop at? At x equal to 2. So for x, it's from negative 2 to 2. How about for y? Who's at the bottom always? As long as this is your scanner, what's the length? Who's at the bottom? This is y equal what? X squared. So from x squared at the bottom, who's the top? We know as long as I'm here, y is equal to 4. So this is up to 4. That's it. We just finished setting up the integral. Now we start the integration from inside. This is equal negative 2 to 2, x squared to 4. Now, what's the integration of all of this? Nothing. This is all constant. So we only integrate dz. What's the integration of dz? Z. So this is x squared plus y squared are constants. Then z from 0 to 4 minus y. Then we say dy dx. Now we replace z with 4 minus y. So this is equal to negative 2 to 2, x squared to 4, then x squared plus y squared, and we replace it with 4 minus y. And then, of course, minus 0, you replace it with 0 next, but we don't have to put the 0, and we say now what? Dy dx. What do we do now? We expand this, negative 2 to 2, x squared to 4. Now multiply 4 by everything here. So you have 4x squared plus 4y squared, then plus or minus x squared y minus y cubed, because y cubed times y is y cubed. All of this dy dx. Now what do we integrate for? We integrate for y. So this is equal to the integration of negative 2 to 2. The integration of 4x squared is 4x squared y. What's the integration of this? Plus 4y cubed over 3. What's the integration of this? Minus x squared y squared minus y to the 4 over 4 dx. Sorry, yeah. Should put the limits of integration first. This is from x squared to 4. Then what do we say? We say dx. Now, this is equal to the integration, negative 2 to 2. Let's put the 4 for the y. Don't forget we're integrating with respect to y. So 4 times 4 is 16x squared. Then put the 4 here. 4 cubed times 4 is 4 to the 4. 4 to the 4 is 64. 16 times 16, I think 64 over 3. Minus, put the 4 here. 4 squared is 16. X squared minus, put the 4 here. It's going to be 4 to the 4 over 4. 4 to the 4, so 16 times is 64. So this one, let me check here, 4 to the 4. I think I got this one incorrectly. We have 4 raised to the power 4, 256. This is not 64, this is 256. All right, so this is 64, and then we say this one is from That's it. We did the 4 actually. Now let's put the x square. My apologies. All right. So all I did now, yeah. So all I did, I plugged the 4. Then what do we say? Minus. Now we put the x square for y. X square with x square is x4. So 4x to the 4. Then put x square in here. You get x to the 6. So minus 4 over 3. X squared to the power 3 is x to the 6. Then you put x square here. So x to the 4 minus x. So this is plus x to the 6 for that part. Put it here. 2 to the 4 is 8. So plus x to the 8 over 4 dx. Now what do? We integrate all of that with respect to x, guys. But probably we can simplify. So for the simplification, we can remove those and proceed. So I'm going to start with here, equal to 16x squared minus 16x squared, they cancel. And then what do we have? X to the 6 minus 4/3 x to the 6 with this one. So this is minus 1 1/3, and 1 is minus 1/3. So this is the integration from -2 to 2 of negative x to the 6 over 3. So those now are finished. Then what do we have? We have minus 4 x to the 4. There is nothing. So minus 4x to the 4. And then, so this is finished too. Then you have x to the 8 over plus x to the 8 over 4. And then you have plus 256. Okay, I'm not sure if this is divisible by 3. It's not. So I'm going to say here, we'll move this one. And we have plus 256 divided by 3 minus 64 dx. Now we integrate with respect to x, guys. What do we have? We have minus x to the 7 over 7 with 1 is 23, minus 4 over 5 x to the 5, plus x to the 9 over 36, plus 256 over 3x minus 64x. All of this is from -2 to 2. You plug those two numbers and you get the answer. All right, simplify all of that and you get, I think it's a big number, 128 over 3. 100. All of this will lead to 128 over 3. I'll leave this one simply because you're going to put the 2 and then the -2. But at least my point was, the focus is how do I set up this, right? The graph, how does the graph look like? What does the formula look like? And what are the dimensions of x, y, and z? All right, as I said now, triple integral, you're free to set them the way you want. You can make it dz, dy, dx. You can make it dz. You see here, definitely this is type 1. Here, this is type 2 because dx, dy. Look, now I changed. But look what happens in every case. Here, this is the height of the solid. So it's on the z-axis from z equals something to z equals something. That means the solid here is standing on the xy plane. Same thing here. The solid is standing on the xy plane. Now, this is the height. So it's on the y-axis, and the solid or the object is sitting on the xz plane. Same thing here on the xz plane. Here, the solid is standing on what? On the yz plane. Same thing here. Okay, guys? So you have to know You have to know what is the height of the solid from X to what, and then where is it standing at. Alrighty? So this is the situation, guys, we are dealing with. So in this case, those two guys here, if you look at the three-dimensional space, the solid is standing here. This is our region R. It's here on the XY plane. In these two, if I change the color, these two guys, notice that it's dz dx or dx dz. So your solid is going to stand here. This is where the solid is standing on. It's on the zx plane. And then it's taken the dimension where? On the y-axis. The dimension here is what? On the x-axis. The dimension here is what? On the y-axis. These two, last two here, the last part is the following. Where's the stand? It's on the YZ. So where's the YZ? So this is where the stand is. The body is standing here and it's moving in which direction? In the x-axis direction. So this is your base. This is your base here, R. This is the base here, R. This is the base here. You see the direction, how it goes? This is what it means when I set them like that. Alrighty? Okay. So for example, change the order of integration for this integral. This is the question originally. I want to change it from dz dy dx to dy dx dz. Complete. Let's see how do we make the change, guys. So this is not an easy task. So let's look first at our original question. This is dz, guys. From where? So this is from z equals 0 up to z equal to 3 minus half x minus 3/4 y. Then I know now I am in what? My base is where? Is in the xy plane and the height is on the z plane. Here, guys? Where is z equal to 0? Z equal to 0 is what? Is the xy plane. This is, by the way, z equal to 0. It's the xy plane. So I am going to start from z equal to 0 and go somewhere up. Okay, what does this look like? Look at this equation. I'm going to multiply it by 4, guys. Why 4? Because I have 4, 2 here. So let's multiply by 4. What do we get? We get 4z is equal to 12 minus 2x minus 3y. Move xy into the other side. Now you have 2x plus 3y plus 4z is equal to 12. So all I did multiply by 4 both sides so that I make it with no fractions. Do you remember the graph of this one? If we let x equal y equal 0. So what do we get? We get 4z is equal to 12. So z is equal to 3. Here is 1, 2, and 3. That's the thing. So this is x0, y0, and z3. Now let's go to what? X equals z equal to 0. So who survived? The y. So you have 3y is equal to 12. So y is equal to 4. Here's 1, 2, 3, and 4. This is on the y-axis. This is 4. So this is 0, 4, and 0. Now finally, you let y equal z equal 0. So we have 2x is equal to 12, which implies that x is equal to 6. So here's 1, 2, 3, 4, 5, and 6. Here, 6, 0, and 0. Now what do? We connect those with the straight line. Doesn't look that straight line. Okay. We have a pyramid, guys. Standing where? It's standing on the XY plane. We are standing on the XY plane because it's dz, dy, dx. Because dz, so this one is starting from z equal to 0. By the way, this is z equal to 0. Or I should do it this way. From the bottom, this is z equal to 0. As long as you're at the bottom, this is z equal to 0. Okay. Now we go up. Where's the surface, by the way? The top is, you see, it's that side that's coming in your side. You see that thing in the pyramid? Okay, if you are here, what is this z equal to? Z in this case, it's given to me. Here it is. Which one I took here. So this one z is equal to 3 minus half x minus 3/4 y. You see, this is now the bottom and the top of the surface. Now, where's my base? dy dx. I'm going to take this one here on the side and see how it looks like. Now, on the x, it's 6. Here's the 6. On the y, it's what? It's 4. So here is 1, 2, 3, and 4. This is 4, and then we can connect those. So what did I do? I took my region here. Now, it says dy dx. So this is a region of type 1. So what do I have here, guys? We have a vertical light. So the scanner is going to start what? Vertically like this. From where? From x equal what? 0, isn't it? It's going to keep on moving to cover the whole region. And it's going to stop here. What is this? 6. This is why you see dx is from where? From 0 to 6. How about for y? What's the length? Who's at the bottom? When you look at this scanner, this light, when it's moving, it's always at the bottom. What is it touching? This is y equal to what? 0. Here is y equal to 0. Do you see that? Up to what here? Y equal to what? Now look carefully at this. When you are actually here, we know as long as we are here, in this equation, what is z? Z is equal to 0, right? So look at this. As long as you are here, we have 0 is equal 3 minus half x minus 3/4 y, isn't it? As long as you are here, this is what you have. You are in the xy plane. This line is in the xy plane. So this is how you write your equation. Okay, let's solve for y, guys. I'm going to move minus 3/4 to the other side. So 3/4 y is equal to 3 minus half x. Now I'm going to solve for y. So I'm going to multiply the whole equation by 4/3. So y is equal. When I multiply 3 by 4/3, 3 goes with this 3. So I have 4 minus 4 with 2 is 2. So this is minus 2/3 x. And this is, guys, what you see here. You see that one? 4 minus 2/3 x is exactly this. So this is 4 minus 2/3 x. This is the top. As long as I'm moving the scanner, it's touching this line. What is this line? This line is when z is equal 0 in the equation because it's in the xy plane. And this is, guys, what he's giving me. So where is my base? This is my base. There, this is the base. And the black lines is our what? Is our surface, the top. Now, what does he want to do? He wants to change it to dy dx dz. So what do we do in this case, guys? Now, where is my base going to be? In the what? In the xz plane. Here is z, guys. So now I'm going to go to the color. Let's choose a color that is green. Now, here, this is our base. It's in the z x plane. So my base now is going to be here, guys. I am now shifting to this. That's my base now. Where is the height? So let me go to the here and make the same graph, guys, so you'll be more accurate. Here it is. we know that Z was up to what? Z is up to 3, Y 4, 6. Okay. This is 1, 2, 3, 1, 2, 3, and 4. 1, 2, 3, 4, 5, and 6. And we have this shape. So now what's going to happen? This is my base. So let's put that greenish thing. This is our base. This is R, by the way. This is the base. Where is the height? The height is in the Y direction. Remember that? It's going to be in the Y direction. Where is the Y direction? Here is the Y direction. So, or you can say from this, we're going up. Another way to graph it, rather than doing this, we can do the following. We can go like this. See what I'm doing now? This is the height. What is this here? On the base, we know that Y is what? Y is 0. This is the base now. You are now on the XZ. You are on the XZ plane. Here, as long as you are here, we know this is Y equal to 0. Up to what? If you are touching this red Z, what is this Y here? You know, as long as you are here, what do we know about the value as long as you're here? Then definitely you're moving in the direction of the Y. So what should I write here? I should get the Y from this one. What's Y equal to? Okay, look at this. What do we have? When we started here Z, we know that Z is equal to 3 minus half X minus 3/4 Y. This is when we were in this height, Z. But now I need in the Y form. So what do? We move 3/4 to the other side. So 3/4 Y is equal to 3 minus half X. And I'm going to move Z to the other side, becomes minus Z. You see, I'll now replace it with Y. Divide the whole equation by 4/3. So what do we get Y equal to? If I multiply by over 3, you get 4 minus 2 with this one goes, so 2/3 X minus 4/3 Z. This is Y, guys. So it is going to be 4 minus 2/3 X minus 4/3 Z. So now my integration is going to be triple integral. We are going to start according to this F of X, Y, Z. He says start with dy. Okay. So the solid is going to the right now in the Y direction. So the base is here, the green base. At this one, what's Y? Starts from 0. And when you go through the object, what's this top? It's this one, guys. So up to 4 minus 2/3x minus 4/3 Z. This is, guys, the dimension on the Y direction. All right, now, what do we do now? We take our base, because I need to see what to write. He says, write dx dz, okay? Dx dz. All right, now, look what I'm going to do, guys. I'm going to take my region, and I should take it actually green. And now it's between X, which is 6, and this one, not Y. This is Z now, and Z is 3, and X is 6. Let's connect these two, guys. It says dx dz, guys. Is it region of type 1 or type 2? Look at this, guys. When I say dy dx, this is a region of type 1, isn't it? So if you have the same shape, so it's going to be like this. So when I say dy dx, it's like this. So it's a vertical, this. And when I say dx dy, this is a region of type 2. And the graph would look like what? The sector is going to go this, and it's going to go in that direction. So here, we go this direction. All right. So whoever comes last, okay, so when I say dy dx, it's vertical. I have dx dz. So it's similar to that. This is region of what? Of type 2. So my scanner is going to be what? A horizontal scanner. You see the point? This is the trick. So when I say dy dx, because it's dy dx, because it ends with dx, so the scanner is going to be vertical. The sector is going to be vertical. If it's dy, it's going to be horizontal. It should be vertical on the y-axis. Since this is dy dz, so the scanner has to be vertical to the z-axis. So this is it, and it's going to keep on moving up. What does it start with, guys? What? This is z equal to what? 0. It's going to keep on moving till we stop here. What is this? Z equal to 3. So it's from 0 to 3 for the z part. All right. From the left, this is x equal to what? Definitely 0, isn't it? This is z equal to 0. So for x, we start with 0. How about this one? Remember here, as long as you are on this, by the way, this is this line. The green line is this line. As long you are here, what's y equal to? 0. But what's the original equation, by the way? If you look at this one, this is what? This is our original equation, by the way. And we are going to take y to be what? 0. So what am I left with? Z is equal to 3 minus half x, correct? But this one, it shouldn't be z as a function of it should be x as a function of z. So move minus half to the other side, so it becomes half x is equal to 3 minus z multiplied by 2. So x is equal to what? 6 minus 2z. So this is up to 6 minus 2z. That's it. Those are the boundaries when I switch from the xy to the xz plane. All right, guys. So this is how you convert and you change the order of integration. All right. And it's been solved here. And finally, we got the same that you see here. All the results are exactly here. And this is the actual nice graph of the function. All right, now. Let's do something about cylindrical coordinates. All right, guys. Cylindrical coordinates, which is the same as the polar coordinates. Let me give you, let's suppose, let's plot a point x, y, z in this. This is y, by the way. This is x and this is z. How do you plot the point? You go on the x-axis. Let's suppose that this is x. You go to the y-axis, I don't any distance. So let's suppose here it is. This is y. What do we do? From the x-axis, we take a line horizontal to the y-axis. From the y-axis, we take a line parallel, sorry, to the x-axis. So they will meet at the point what first? X and y. Now, how do I plot the whole point, x, y, and z? Let's go to z. Let's suppose that z is here. Now, what do you do? From the y-axis, you go all the way up to that z. And then what do? You take a line parallel to the x-axis. Then you go from here all the way up. They will meet here. This is now the point x, y, and z. So this is, guys, how you find your point. X, y, z. This is how you plot it. All right. This is a point in what? In rectangular coordinates. This is what we call rectangular coordinates. If it's two-dimensional, we call it Cartesian coordinate. Now, in 3, we call it rectangular coordinates. Now, I'm going to present this one in something called cylindrical presentation, cylindrical coordinates. What do I mean by cylindrical coordinates? I'm going now, guys, to connect this point with this line, and I will call this line R. Remember the polar? Now, we know that this one, by the way, is a right triangular thing. This is a right triangular. And let's suppose that this angle is theta, the angle between the x-axis and that R. If you remember the polar coordinates. Now, this one is definitely y, and this is x. All right, now what do we know about theta and the relation between theta and y? We know that we can say here that y is equal to what? Remember, y is the opposite of theta. So y is equal to what? The hypotenuse, or you can say y over r is equal to what? Sine theta, isn't it? Sine theta is the opposite over the hypotenuse, which implies that y is equal r sine theta. Similarly, if you look at x, this is x, by the way, it's adjacent to theta. So we know that x over r is sine theta, is cosine theta. So that means x is equal r cosine theta. All right, now, what happens when I divide y over x? We know that y over x is what? Is tangent theta, isn't it? But when I divide y over x, that means I'm dividing r sine theta over what? R cosine theta. This goes with that. We have sine over cosine, which is what? The tangent theta. This implies if I need to get theta, what do? I take tangent inverse of both sides. So here is theta. Just follow me of what I'm going to do now. How do we get r, by the way? R is what? R, the radius, is x squared plus y squared, isn't it? Is x squared plus y squared is r squared. So that means r is equal to the square root of x squared plus y squared. Now, how am I going to reach to this point, x, y, z, using the cylindrical? I can do it in another way. What do? I'm going to go all the way down and find the distance between the point xy and the origin and call it r. So look what happened. And this is the same as this. So this is actually is going to come here. So the circle is going to move and it's going to come here. So now we are here. Measure the distance between the x-axis and r, call it theta. You're going to find it using this. So if I take this r, which is theta distance away from the x-axis, I will come here definitely. Now, how do I go up? Go up with what's this distance? This distance is what? Is definitely z, isn't it? Go up z. This is how you present it. So every cylindrical coordinate can be presented with r, theta, and z. Okay? This is the same thing as x, y, and z. This is what? In the cylindrical, and this is in what? In the rectangular. So a point in the rectangular is presented with x, y, z. How is it presented in the cylindrical? It's presented by r, theta, and z. What's r? R, it's the square root of x squared plus y squared. What is theta? It's tangent inverse y over x, and z is the same z. So if you take this r, that is theta away from the x-axis, and this will take you to xy. How do I go up? The distance to go to this point is z. Just go z up and you are on the point xyz. So another presentation of the point xyz is r, theta, and z in the cylindrical. So how do we go from cylindrical to rectangular? Very easy. What do we use now? Sorry, how do you go from rectangular to cylindrical? So we say rectangular to cylindrical. The rectangular is x, y, and z. What's the rectangular? R, theta, and z. How do I go from here to here? It's easy. What's r equal to? X squared plus y squared. What's theta equal to? Tangent inverse y over. Done. This is how you go. And then what's z equal to? Z is the same z. Z is z. No change in z. Okay, if you want to go back now from r, theta, and z to x, y, and z, from the cylindrical to rectangular, what do we know about x? X is equal r cosine theta. You see, you have r and theta. What's y? R sine theta. What's z? Same z, doesn't change. So this is how you go from cylindrical to rectangular. And this is what I'm saying in this slide, guys. And this is what I'm saying in this slide. Let's look at this example. He says, convert this cylindrical coordinate into rectangular coordinate. What's a cylindrical? He's giving me 8 pi over 3 and 7. Be careful, he's saying the cylindrical. So that means r is 8, theta is pi over 3, and z is 7. What do I need to convert it to? To rectangular. In the rectangular, what's x equal to? R cosine theta. And what's r here? 8 cos pi over 3. And we know that cosine pi over 3 is half. So this is 8 times half, which is 4. Let's look at y. Y is r sine theta. All right. Now, what's r? 8 sine pi over 3. We know that sine pi over 3 is root 3 over 2. So you have 4 root 3. Now we have x and y. Who's left? Z is the same thing as z, which is 7. So that means the point 8 pi over 3 and 7 in the cylindrical converts to what? 4x, 4 root 3y, and 7z. You can graph it easily on the xy plane, no, xyz space. This is a similar thing. I'm going to skip it. Let's go to this one. Convert from rectangular to cylindrical now. So what am I given here? Root 2 minus root 2 and 1. Don't forget, this is x, this is y, and this is y, because he's giving me the rectangular. How do I get to the cylindrical? What do I need? I need r, guys. What's r? R is the square root of x squared plus y squared, which is the square root. The square root of 2 squared is 2. The square root of negative root 2 squared is also 2. So this is the square root of 4, which is 2. So r is 2. What's theta? To find theta, it's tangent inverse y over x, which is tangent inverse. Y is minus root 2 and x is root 2, which is tangent inverse of negative 1. Now, tangent inverse of negative 1 is going to be in the fourth quadrant, which is actually, you can say minus. So you can take the minus out. What's tangent inverse 1? It's pi over 4. That's the angle, guys. Done. I have r theta. So what do we say? What's z? Z is the same z as 1. Nothing here changed. So that means root 2 minus root 2 and 1 in the rectangular coordinates converts to what? To 2 minus pi over 4 and 1 in the what? In the cylindrical coordinates. All right, now. We're now going to integrate, same thing, by the way, integration over three-dimensional surface. But today we're going to use what? Remember the polar, or what we call the cylindrical. And remember in the polar, we changed to r dr d theta, right? So dz stays, and we say r dr d theta. Z is the base and the top. R theta, you know the r is the magnitude of that radius, and theta, how far it is from the x-axis, and you put your coordinates and you finish it. If there is no f here, then what do we have again? This f is 1. We have what? The volume of the solid in three-dimensional space. Okay, Let's take a good application on that. Remember that the volume of a sphere is what? Of radius A is 4/3 pi a cube, isn't it? This is a standard. I'm going to use today's cylindrical coordinates to prove that, to show that really this is the volume. So we are going to take, to prove this one to you guys, I'm going to graph not the whole sphere, but half of the sphere. Only half sphere, semi-sphere. A sphere of radius A. So this is A, negative A. And here you can go all the way down like that. And in the back, here's, guys, sphere of radius A. Of course, this is A, this is negative A, this is A, and here it's negative A. It's a sphere. It's a dome. All right. What do we do to find the volume? The volume is equal, we said, triple integration dV over D. What's D? The whole thing. But I'm talking about only half sphere. So I'm going to find the volume of what? Half sphere. Not the whole sphere, but half of it. All right, what do we do, guys? Now, let's look at this. The sphere is standing where? It's standing on the XY plane, isn't it? It's on the ground. So since it's standing here, if you look from the bottom, what is this? If you go through the bottom, what is this one? This is a circle in what? In the XY plane. We know here that Z is equal to what? 0, because you are on the ground. There is no, you're not going to go up, right? So you are at Z equal to 0. So this is equal to triple integration. I'm going to start with dz, which starts from 0 to what? What is this? This is z equal to 1. Remember, whenever you have the upper sphere, we know that the equation of the sphere is what? X squared plus y squared plus z squared is equal a squared, isn't it? This is the equation of a sphere. Move everything to the other side. So z squared is equal to a squared minus x squared minus y squared. So z is going to be what? Plus minus square root of a squared minus x squared minus y squared. But I need only the upper. So what's this? This is the square root of a squared minus x squared minus y squared. But this can be written as what, guys? This is as a squared. Take the minus out. So what do I have? X squared plus what? Plus y squared. Now in polar, guys, I'm going to use the polar. So what do we say? R, then dr and what? And d theta. Correct? This is the formula for finding the volume using the cylindrical. Cylindrical says r dz dr d theta. Okay, z is from 0 to z equal to what? Isn't this a square? We know in polar, we know that a square, so we know that x square plus y square is equal r square, isn't it? So this is a square minus r square. So the z starts from 0 to a square minus r square. So this is the bottom and the top of the surface. Go from the bottom, z equal to 0, to the top, which is z equal to, this is the equation of the top, but I can factor out the minus, and we know that x squared plus y is equal to r squared. Now what do we do, guys? We're going to take the base. All right, let's take the base. What's the base here? We know certainly on the xy plane, our base is a circle of radius a, right? It's a circle of radius a. This is our base. All right, so what do we do now? We can take, sorry, let's keep it. We're going to take R, leaves R, starts from where? From 0, ends at what? At A, isn't it? So R is going to start from 0 to A. How about theta? To cover the whole circle, remember in the polar, you have to rotate how much? Full rotation. So you start from theta equal to 0 up to 2 pi. That's it, guys. We set it using cylindrical coordinate. It's like the polar, same thing. But here we have height. Remember in the previous one, the height was inside in the previous sections. Now the height is where? On the integral. All right. Now I'm going to erase that one and finish the integration and see what we get. What do we start with? Usually we start from the inside. So this is equal integration from 0 to 2 pi. Integration from 0 to A. Now, we are going to integrate with respect to Z, guys. What's the integration of dz? It's Z. So you have RZ, and this is from 0 to A square minus R square. And then what do we say? dr d theta. Now we plug the top one. So this is the integration from 0 to 2 pi. Integration from 0 to A. Replace Z with this one. So you get square root of A square minus R square. And then you have R dr d theta. Correct? Because when you plug now the 0, you should plug the top one, then minus the 0. I don't have to put the 0, and this is what's left. Now, what do we have to do? We have to integrate from the inside. How do we integrate this one? Even though we've done it so many times. So I'm going to take my space here. I will see how do we integrate such a function. Okay, how do you integrate square root of A square minus R square, then R dr? We did it many times. So you let U equal to what? A square minus R square. So du over dr, the derivative of A square is 0. The derivative of this is minus 2R. Bring dr here. So du is minus 2R dr. In the question, I have only R dr, so I'm going to divide by negative 2. So what's my question going to be? This is the integration of square root of u. Then R dr is du over what? Negative 2. Take the minus half outside. Now what's the integration of u? This is u to the half. Becomes u to the 3/2, then 2/3. This one cancels that. And you have minus u 3/2 over 3, which is negative. What's u? U is A square minus R square. So the answer is minus A square minus U square, all, let me put it down. So this is equal to negative A square minus R square to the power 3/2 over 3. That's the answer. So I'm going to copy it here. So this is the integration from 0 to 2 pi of minus, okay, minus 1/3 can go out, by the way. So what am I left with? A square minus R square to the power 3/2. And this is from 0 to A. And then d theta. All right, guys, now let's plug what? Instead of R, we're going to put A. So if we put A, what do you get? A square minus A square is 0. So this is equal to minus 1/3. Integration from 0 to 2 pi is 0 minus. Put now the 0. What do you get? You get A square to the 3/2 d theta. Now, this is equal to this minus with this minus is a plus 1/3. Now this 2 goes with this 2. You have A cubed goes out. What am I left with? Integration from 0 to 2 pi of d theta, which is equal to 1/3. The integration of this one is theta from 0 to 2 pi. Now, what do we plug in? So this is 1/3 a cube. Plug the 2 theta first, 2 pi first. Here it is. Minus the 0. You don't have to put the 0. So this is the answer. So the answer is 2/3 a cube pi. This is, guys, the volume of half sphere. So for the whole sphere, what do you multiply with? So this is what? Don't forget, this is half sphere. So we can say that the volume of sphere is, multiply this by 2, you get 4/3 a cube pi. And this is exactly what you have here, guys. And this we just proved by triple integration. This is what I did. I looked at the shape. I have a surface. The bottom is z equal to 0 because it's standing on the xy plane. The top is z equal to square root of a square minus r square. Put it as a limits for the z. And then for r of theta, I looked at the base. It's a circle. I took a radius of that circle, which is from 0 to a. I rotated 2 pi. That's it. You get the volume. All right. All right. So I will just take a break and come back in a minute. So stay around. All right, guys. Now he says, if this is your f of r theta z, so you know this is cylindrical, is equal to r, then integrate f over the region D, where D is the region bounded by these curves. This is 1, and then all of those. Now, let's take the first one. Z equal square root of x squared plus y squared. If I square both sides, guys, what do we get? Z squared is equal to what? X squared plus y squared. Remember, this is what? This is the equation of the cone. So let me graph the cone now. So we are going to start with the cone. Here is the cone. Gonna go up. Okay, and then we're gonna go up to z equal to 1. Let's suppose that this is 1, guys. When I say z equal to 1, what do I mean by z equal to 1? Z equal to 1 is a plane. Z equal to 1 actually is a plane. This plane is gonna come and cut what? That cone. What's the result of the cut? This is the result of the cut. So now I have the cone. You see, the cone is going up. Z equal 1 is going to come. It's a plane that is going to cut it. So this is the final result of the graph. It's a cone that is cut this way. If you go like this on the x-axis, so here and in the back, you get this one. But now what's happening, guys, is the following. Also, it's cut by x equal to 0. What's x equal to 0, by the way? X equal to 0 is the YZ plane. So you see here, this back part, all this back is going to go away. I don't want it. We don't want all of this. And y equal to 0 is the XZ plane, which means also this, I don't want it. So I'm going to cut all of this. So who's going to survive? Let me show you in red who's going to survive from all of this. So this is the leftover, guys. When I cut all of those that I showed you, so this is what's left from the cone. And this is what I need. Just that. All right. And this goes straight down to here. And this is the left of the cone. So we have only 1/3 of the cone, guys. And everything else is going to go away. So I'm going to erase the rest of the colors. I don't want this. I don't want that. I don't want that. None of this is needed anymore. Okay, see the result? This is the final result after I cut what I don't need. All right? Perfect. Now, what do we have? This is actually the surface from the outside. All right. If you're standing here on the ground and you look up, you're gonna cross the shape from here, right? What is this Z equal to? Isn't this that? This is the base, right? It's the cone. So this is equal to the square root of x squared plus y squared. But in polar, what is this? This is the square root of r squared, which is what? R. So the bottom, so look at the volume now. So now he doesn't want the volume. He wants to integrate. So he wants to integrate f of r theta, which is r. Then what do we say? R dz dr d theta. This is f that he's giving me. Z starts from where? Bottom, R. Up to this. This is, by the way, Z equal to what? When you go from here, what's Z equal 1? This surface here. This is Z equal to 1, isn't it? So this is from R to 1. So when you go, if you're standing here at the bottom, you look up, you will see that surface. And this is from Z equal to the cone. So from the bottom, you see this, the cone. Okay, get inside and go from the top. Who's the ceiling now? This is Z equal to 1. So this is the out. Now let's look at the base, guys. When I bring this one down to the base, to the ground, where does it go to? We know very well that this is a circle of radius 1, isn't it? This one is the cut. This is a cone. So when we cut it, it's a circle. Circle of radius what? 1. So I have a circle of radius 1. So this is a circle of radius 1. This is the projection. So if you flip that cone, it will stand on this one, which is a circle of radius 1. So I'm going to take it and graph it here. But it's only on the y-x positive. So only this one. So here's the graph, guys. This is 1 and this is 1. This is my region R. This is the base. What do we do now? Take any what? Take any R. What's the distance? From 0 to what? To 1. So R is from 0 to 1. Then to cover the whole region, we're going to move this way to cover the whole region. Where do we stop at? We stop here. What is this theta here? You know, theta is going to start from here, which is 0, up to, you know, this is vertical. We know that here it's pi over 2. So up to pi over 2. That's it, guys. This is how you integrate that one. This is the finishing of this shape. Now, what do we start with? We start from inside. What do we have? We have the integration from 0 to pi over 2. Integration from 0 to 1. Now, this R with this R is R squared. We're not going to touch it because it's a constant now. We're going to integrate with respect to Z. What? What's the integration of Z? dz is Z. From R to 1, then dr d theta. Now what do? We plug the 1 first. Put Z1, you get 1 times R squared is R squared, minus, replace Z with R with R squared is R cubed, then dr d theta. Now we are going to integrate with respect to the inside, which is dr. So this is equal to the integration from 0 to pi over 2. The integration of R squared is R cubed over 3. The integration of R cubed is R4 over 4. And this is from 0 to 1 d theta. Now plug the 1, please. You will get 0 to pi over 2. If you replace R with 1, you'll get 1 cubed, which is 1 over 3, minus 1 over 4. Minus, if you put the 0, you get 0. We're not going to plug the 0, and then d theta. Now you have 1/4, and 1/3, that least common is 12. 12 divided by 3 is 4, so you have 4 minus a 3, which is 1 over 12. I will take it out. I'm left with the integration from 0 to pi over 2 of d theta. And this is equal to 1 over 12. The integration of this is theta from 0 to pi over 2. So this is equal to 1 over 12. Put the pi over 2 first, minus 0. So the final answer is pi over 24. This is, guys, the result of the integration. All right, let's do this one now. Find the volume now of the solid bounded by the graphs of the given equations. I have two equations to deal with. Okay, let's look at the graph of this one, guys. So I'm going to start with the dark ones to make the coordinates. Here's the y-axis, and here's the x-axis, and this is the z-axis. Now, what do we have? Start with the first one, y equal x squared plus y squared. We graphed it so many times. This is a paraboloid, open upwards. This is paraboloid. It looks like this. Goes all the way up. And then from here also, it goes all the way up. So we can go up here. And then probably we can connect those. And here's our paraboloid. Okay, and in the back here, we erase that one on the x-axis. We can graph it in a better way. Okay. This is the graph. Okay, so we have a paraboloid. That's the first one. The second one is 2y equal x squared plus y squared plus 4. Divide by 2, so y is equal to x squared plus y squared over 2 plus 2, isn't it? So this is the same one, by the way, but it's shifted 2 units up. So let's go to 2. Here's 2. Same paraboloid, but it's going up. So here's the other one. I have another paraboloid here that is going up. So that's the other one. So let me put the other one in a different color. So let's put it in red. Okay. And this actually with red goes like that. And from the other side, you go all the way up. So this is two paraboloid now. They are one inside the other. Now I need the region between them. So I'm talking about this upper paraboloid. Okay, so we have this upper paraboloid. The top one, the result of the intersection. The cup now is moved up to you, 2 units up, and this is the result of the intersection. They're gonna meet somewhere here. Perfect. Now, we need to find the volume of the solid. What's the volume equal to? It's equal to the triple integration of dV over d. But I'm gonna use now what? Common sense. Look at what's happening, guys. Let's look at the bottom of this one. Okay, let's look at the bottom of that one. Just 1 second here. Okay. All right. Now, so this is the top. So where is my final region? Let me put it in a different color now. So my final graph is going to be that part. So if you are standing at the bottom here, guys, on the ground, you're going to look through. What do you see? You're going to see the bottom one. The bottom what? Paraboloid. The bottom one is what you're going to see, right? So you're going to come from inside. So you will see the bottom one. So you're going to cross it. What is this? The bottom one is Z equal to x squared plus y squared. which is z equal to what? R square. So this is equal to the triple integration. I'm going to triple integrate. I'm going to say r, then dz, dr, d theta. Z is going to start from the bottom one, which is r square. Now you're going to go, and by the way, this is hollow, empty. This is empty now, as you see. Now you're going to go inside, and then you're going to go out from here, and then you're going to go inside. So now this is the second one. So you start with the inside dome, or okay, that cup, and then you go to the, you cross the second one on the top. Who is this one? This is z equal to x squared plus y squared over 2 plus 2, which is equal to r squared over 2 plus 2. So this is up to r squared over 2 plus 2. This is from the bottom to the top. Now, how about r dr d theta? Now, what's the intersection between those two guys? If you look at these two equations, what's the intersection here between them? Okay, so let's take this on the side here. We have y is equal to this and y is equal to that. So what does that mean? We're going to have x squared plus y squared equal to x squared plus y squared over 2 plus 2. Right? This is what we have for the intersection. So multiply the whole equation by 2. So what do you get? You get 2x squared plus y squared is equal to x squared plus y squared plus 2. Move this x squared plus y squared to the other side. What do you get? You get minus that. So now we have x squared plus y squared is equal to what? To 2. I forgot actually when I multiplied by 2, this is supposed to be 4. So this is 4. Again, the left side is equal to the left side. So the right side must be equal to the right side. Here it is. The right side is equal to the right side. I multiply the whole equation by 2. I got this. I move this to the other side. Becomes one of them. 1x squared plus y squared is equal to 4. And this is the equation of what? Circle of radius 4. So this is circle of radius 4. Where is it? Here it is, guys. The intersection is here. This is a circle, not my apology. It's a circle of radius 2. It's a circle of radius 2 because this is 4. So let me drop it down on the XY plane, guys. When I drop it, here is our circle. We have a circle of radius 2. So this is 2, 2, and in the back here, that's a negative 2. This is my region. If I take it here on the side, when you have a circle of radius 2, take r, starts from 0 to 2. So r is going to start from 0 to 2. Now to cover the whole circle, what's going to happen? So this is going to be from 0 to 2 pi. Now what do? We start the integration from inside. So this is equal to the integration from 0 to 2 pi. Integration from 0 to 2. Now the integration of dz is z, and there is r already. So this is r z, rz from r square to r square over 2 plus 2. Then we say dr d theta. Now what do? 0 to 2 pi, 0 to 2. Now we replace z with this. So it's r times r squared over 2 plus 2. Minus, we replace it with here. What do we get? We get r cubed dr d theta. Now we do the integration internally from the r. So this is equal to the integration from 0 to 2 pi. Integration from 0 to 2. Let's multiply this. This is r cubed over 2 plus 2r minus r cubed dr d theta. Again, we're playing with the inside. So this is 0 to 2 pi. R cube over 2 minus R cube is minus, let's say it's 2R minus R cube over 2 dr d theta. And we are integrating with inside, from inside 0 to 2 pi and 0 to 2. Okay, 0 to 2. Now let's integrate, guys. So this is equal to the integration from 0 to 2 pi. Now the integration of 2r, r squared over 2, so the 2 goes away, minus r to the 4 over 8, and this is from 0 to 2 d theta. So this is 0 to 2 pi. Put the 2, guys, you will get 4 minus, put the 2 here, 2 to the 4 is 16, divided by 8 is 2 d theta. And the 2 goes out. You're left with the integration from 0 to 2 pi of d theta. We know that the integration of d theta is theta from 0 to 2 pi. If I plug the 2 pi, I get 2 pi times 2 is 4 pi. And this is actually now the volume of this paraboloid that is bounded below by z equal x squared plus z squared, on the top by the other one, 2y equal x squared plus y squared plus z squared plus 4. So it's the blue region. All right, now let's do this example. Find the volume of the solid bounded by the graphs of the given equations. These are the two equations, by the way. So let's see, what do we have here, guys? We have z is equal to 10 minus x squared minus y squared. We know that the graph of this one is a paraboloid that is open where? Open downwards. And it's shifted 10 units up. So you go to z equal to 10 and you make your paraboloid. This is the x-axis here. So the same thing, you go to the x-axis, you go to the x-axis, and let's see if it's crossing here. So this is the graph. Okay, let me fix a little bit. This is that paraboloid. It's like a sphere, but it's a paraboloid now. Okay, now the other equation is z equal to 1. Where is z equal to 1? It's a planar. Here is 1. Z equal to 1, by the way, is a plane. This plane is going to come and it will cut that thing here. What's the result of the cut? Definitely, when you cut it, you will get what? You will get a circle. Where is my region? It's that region that is bounded between, if I make an x-axis here, so it's going to be like this in the back, and there is something in the front also. So it's the upper one only, guys, only the top one. Okay, it's only the top one. All right, so this is my region. So I'm going to take it here. I will go to z equal to 1. Here, I'm going to make a circle. And this goes all the way to 10 and goes down. So this is 10, by the way. So this is actually our graph. The graph is just that one hanging up there. So far, so good. So this is what we have. Now, what is the result of these two? It's this circle, right? So this circle is the result of these two, z equal to this and z equal to that. So what do we have? Since they have the same z, so we can make the right-hand side equal to the right-hand side. So that means 1 is equal to 10 minus x squared minus y squared. Move x squared, y squared to the other side. Move the 1 here, what do you get? You get 9. So what is this, guys? This is x squared plus y squared equal 9, which is a circle of radius what? 3. I'm gonna drop it down on the xy plane. So that will be our base. This is the base. But my shape is the one that is up here. This is my shape. It's the top. This is the top thing. Now, what's the volume of that? So what do you do, guys? First, I said, imagine you are standing somewhere here. You are here. Go up and look up, guys. What you're going to see, you're going to see this circle, flat circle. When you cross it, what circle is that? This one is z equal to what at this one? At this point, when you graphed it, that was what? Z equal to 1, isn't it? When you cut it as z equal 1. So this is the cut at z equal to 1 here, z equal to 1. So I'm going to say r dz dr d theta. All right. So now z is from 1 to what? Who's this on the top? This is z equal the dome, which is 10 minus x squared minus y squared. But I can take the minus out, which is equal to 10 minus what? R squared. So this is up to 10 minus R squared. This is the top of the dome. What's the bottom of the dome? It's flat, z equal to 1. Now I dropped it down. I got this circle. It's a circle of radius 3, right? 3, negative 3. It's a circle of radius 3. So this is a 3. So what do? We take r now. Here's r, starts from 0 to 3. And to cover the whole circle, you have to make a full rotation. And this is from 0 to 2 pi. I will leave this for you guys to finish it. We've done so many examples. So the answer is 81 over 2 pi. The answer is 81 over 2 pi. Do the same thing. Start from the inside. Integrate with respect to z. The integration of dz is z. And then you plug the top similar to what we did. And you get the answer. All right. Now we have another kind of coordinates called the spherical coordinates. When do we have a spherical coordinates? If our surface is like a sphere thing, a spherical thing. So let's look at this guy's sphere. I'm going to take a point on the surface of the sphere. Take any point. So the point is going to be what? X, Y, and Z. This is in what? Rectangular coordinates. How do I represent this one spherically? Very simple. Connect this point with the origin. Here's the origin. And take this one and call it rho. So you see this rho? This is the distance between the surface of the sphere and the origin, which is the radius of the sphere. Then we're going to measure the distance between that radius and the z-axis. This angle is phi. So phi is the angle between the positive z-axis and phi. So what's going to happen, guys? You have to understand that this phi can go between 0 and pi maximum. So if you imagine the situation here, if I have this rho, and it's on the sphere, when it rotates from 0 to what? To pi, what's the result? So we're going to start from here. This is phi equal to 0. And it will rotate like that. Not rotate, actually, moving all the way down. What is this going to construct? A half disk, right? It's half disk. Now, what happens if I rotate this disk 360 degrees? So if I drop this rho down to the XY plane, projected, this is going to be your OQ. Sometimes we call it R. All right, measure the distance between the positive x-axis and R. Let's call it theta. So this is the distance. So what happens now, if I rotate this theta 360 degrees, that means if this guy rotates 360 degrees, what's going to happen? What do we construct? Don't we just construct a sphere, right? If you make full rotation, what is this going to construct? A sphere, a complete sphere. So when this row starts from 0 all the way to pi, all this complete rotation here, this is going to be a half disk. If I rotate this disk 360 degrees by angle equal to theta, this will construct the what we call the sphere. So if the point is somewhere here, by the way, so what is this? This is rho. Now, let's rotate this one 360 degrees. What is this going to construct? A circle, right? Now, so if you go all the way up and down, what is this going to cover? The whole sphere, right? And this is how it goes. So the spherical presentation of the point XYZ in the rectangular coordinate can be presented by rho, phi, and theta, where rho is the distance between the origin and the surface of the sphere, which is rho. Then this rho is going to can move between the x-axis, the z-axis, positive to the negative. So this will construct phi angle, maximum to pi. Then this, if I make this movement completely, we get a disk. Rotate this disk 360 degrees with angle equal to theta, which is the angle between the positive x-axis and that rho. This will construct what we call the sphere. Now, if I give you the spherical coordinates, if I gave you actually rho, so the spherical coordinate is going to be rho, phi, and theta. If I give you that, can you change it to x, y, and z? Yes, we can. How? Look at this. X here, look at x. Where is x? By the way, x is this one. What is x? X is adjacent to theta, isn't it? So we know that you can say here that cosine theta is x over OQ, isn't it? This is the radius, huh? So we know this in this case. Look at this one here. We know from this one, for x, we know that cosine theta is the adjacent, which is x over OQ, which is r. So OQ is equal to, or x is equal to what? OQ cosine theta. So x is equal OQ cosine theta. But what's OQ? This one is OQ, is the same as that one. And this is what? Opposite to phi. So it's sine phi, right? It's rho sine phi. So it's rho sine phi and then cosine theta. So x here is going to be rho sine phi cosine theta. If you have rho, phi, and theta, you can find x by using this formula. How about y? This is y. Y is opposite to theta. So we use sine theta. We know that sine theta is equal to y over what? Over OQ. So that means y is equal OQ sine theta. But again, OQ is rho sine phi. So here it is. So you have rho sine phi cosine sine theta is your y. How about z? Where is z, by the way? This is z. Z is adjacent to phi, isn't it? So we can say that cosine phi, is the adjacent, which is z over rho. So that means z is equal rho cosine phi, and this is what you have here, guys, from the graph. So if I want to change it to x, y, z, these are the three formulas you need to apply. Let's look at this example. This is spherical coordinates. I have 2 pi over 3 and pi over 6. This means rho is 2. Phi is pi over 3. Be careful, phi is first. And theta is pi over 6. This is in spherical. What it will be in x in the rectangular coordinate? We know x is equal to what? Rho sine phi cosine theta. Rho is 2, sine phi is pi over 3, and cosine theta is pi over 6. And this is equal to 2. What's sine 60 is root 3 over 2. What's cosine 30? Root 3 over 2. This 2 goes with this 2. Root 3 times root 3 is 6. So 3 over 2. And the answer is a 3 over 2. So x is a 1.5. Same thing. Y is rho sine phi sine theta. Rho is 2. Sine pi over 3 is phi. And sine theta, which is pi over 6, which is 2. This one we said the pi over 3 is root 3 over 2. And this one is half. This goes with that. And you have root 3 over 2. This is y, guys. How about z? Z is equal rho cosine phi. Rho is 2. Pi is pi over 3. And y cosine pi is half, and the answer is 1. So we have actually, what do we have here? I have a sphere of radius 2, okay? And phi is just up to pi over 3, and theta is just pi over 6 rotation. This is going to give us about a 30-degree rotation sphere, and pi over 3, which is 60 degrees rotation from the top. I'm not sure if I can do this one here. So take rho equal to 2 and make sure it's only pi over 3 distance, which is 60 degrees from this one. Here it is. Here's rho of radius. This is 2. And the angle here between z-axis is pi over 3. Now we have this sphere. But how much do we, what's the distance between this and the x-axis? It's pi over 6, which is 30 degrees. So actually, I should put it somewhere here. So this distance has to be only 30 degrees. So this one is pi over 6. Or you can project this one down here. So this angle is pi over 6. It's kind of, not easy to visualize this one using this sphere. How do we go backwards? If I give you the x, y, z rectangular, how do you go to rho, phi, and theta, guys? We know that rho is equal to, here's rho, by the way. Rho is equal to this square plus this square, right? This one is z square, and this one is OQ. But this one is the same as that. And this is this square plus this square. This is x square. So rho is x square plus y square plus z square, as you see here. Now, how do we get theta? The same thing, remember? Theta is tangent inverse y over x. How do we get the z? We know that z, remember, z is rho cosine phi. So cosine phi is z over rho. Rho already found, we found it here. Z is going to be found. So this is how you find the value of the phi. So this is what you have. So that means phi is equal to cosine inverse of z over square root of x squared plus y squared plus z squared. That's it. Let's look at this example. Okay, convert this rectangular coordinate, this one, to spherical and cylindrical. Okay, so we have 1, 2, and 7. This is x, y, and z. How do we go to spherical now? So what's rho? It's the square root of 1 square plus the second square plus the last one square, which is equal to the square root of 54. That's rho, guys. And which is 7.35, something like this. Now, what do we need? We need theta. What's theta? Tangent inverse y over x, which is tangent inverse. Y is 2 and x is 1. Tangent inverse 2 is almost 63.43 degrees. That's the theta. How about phi? Phi is cosine inverse z over rho, guys, which is cosine inverse. Z here is 7. And rho is square root of 54. If you do this with the calculator, you get 21.63 degrees. That's it. You got rho, phi, and theta. You've done. So you can say 1, 2, and 7 is nothing but rho, which is 7.35. Phi, which is 21.63 first, then theta, which is 63.43 degrees. All right, now, the last part is how do we apply the spherical integral? So it's a function of rho, phi, and theta. In the cylindrical, we know it's r dz, r d theta. Now, how about in this one? So you're going to convert everything to rho, phi, theta, and you say what? Rho square sine phi, then d rho, d phi, d theta. Rho is the length of the radius of the sphere. Phi is the angle between the z-axis and that rho, and theta, the angle, if I project it on the xy plane, it's the angle between the projection and the x-axis. If this is 1, we can just apply the volume. I'm going to show you how do we apply the spherical coordinates in finding a volume of an object. All right, let's look at this graph, guys. It says use spherical coordinates to find the volume of the solid that is bounded by these two graphs. Let's start with the first one. Z is equal to square root of x squared plus y squared. Remember, this is the upper part of what? Of the cone. This is the upper cone. Here's a cone. Just the upper part of it. Of course, it continues all the way to infinity. And what is this? X squared plus y squared plus z squared equal to 9. This is a sphere of radius 3, isn't it? So we're going to construct now a sphere of radius 3, and I'm going to graph it like this. So it's going to go up to 3, come back here, and goes all the way down. So this is a sphere of radius 3. But anyways, what do I need from that sphere? I need to find the volume of the solid that is bounded by these two graphs. So where is the first? Here's the cone, guys. Here's the cone. And here's the top of the sphere. Bounded by these two, okay? So it's exactly, if I go here and I make that x-axis, so probably he's asking about that cover. So this top thing. Find the volume of this solid. Okay, that's the top of it. So, of course, including all the cone, right? It's the cone that is covered. It's like this diamond thing, right? Looks like a diamond, which you guys have diamonds, all right? So this is a diamond kind of shape. Now, we're going to use what? Spherical coordinates. To find the spherical coordinates, guys, let's find rho. Now to be on the sphere, so I'm going to use a color that shows here. Look at this. I'm going to go to the origin all the way to what? To the sphere. And not only on the sphere, also, here's the point on the sphere. Also, it's the side of my shape, isn't it? The side of the diamond. So what's going to happen now? This is going to find a rho. Give us rho. What's rho? Rho, it's easily equal to 3, right? Because this is a sphere of radius of 3. Then now we know that rho is equal to 3. So now rho is equal to 3. The question is, how far is this one from the positive z-axis? And this is the angle phi, isn't it? That is supposed to be our phi. So look what we're going to do now in this part. We are going to evaluate. I'm just going to use my calculator here. Yeah. Okay. So the radius is equal to 3. Now, what do we know about z? Z here is equal to the square root of x squared plus y squared, correct? This is the value of z. And this is the upper part of the cone. All right. Now, also, from this one, we can say that z squared is equal x squared plus what? Y squared. So what is this now? This is still the cone. But this cone is going to intersect with what? With the sphere. In the sphere, what do we have? We have x squared plus y squared plus z squared equal to 9, isn't it? So look what I'm going to do. But I know that x squared plus y squared is equal to z squared. So what do we have here? So z squared plus z squared equal to 9. So 2z squared is equal to 9. So z squared is equal to 9 over 2. So what's z equal to? Plus minus square root of 9 over 2, which is 3 over root 2. I'm not going to take the negative because I need z to be positive side only. So in this case, this is the maximum they're going to reach to is this one. So z is equal. So z here is only 3 over root 2. Okay, that's the value of z. To find phi, guys, what do we know about phi? We know that the formula says that z is equal to rho cosine phi, isn't it? Z already root, so it's a 3 over root 2. Rho, we found it to be 3 cosine phi. Divide by 3. So cosine phi is equal to 1 over root 2. What's the angle that gives me 1 over root 2? Then we know that phi is pi over 4, 45 degrees. So this guy is pi over 4 away from the z-axis. Clear? This is what we have. How about the theta? Okay, now what about the theta here? You see, the rotation to cover the whole thing, the whole sphere, definitely theta has to be from where? Theta is definitely from 0 to what? 2 pi, because I need to cover the whole thing. So if rho make a full rotation, it's going to rotate 360 degrees. So what's the volume here, guys? The volume says it's triple integration of dv over what? Over d, which is equal to triple integration. What do we start with? Rho square sine phi. Rho square sine phi, then d rho d phi d theta. This is the formula. Now, rho is from where to where? We found that rho is a 3. So it starts from 0 to what? To 3. So rho is from 0 to 3. How about phi? Phi starts with, remember, phi is the angle between the z-axis, which is 0, up to pi over 4. To cover the whole thing, theta is going to be from 0 to what? To 2 pi. You can do it this way. And that's it. Then you make your integration. How do we integrate this one? We start from the inside. So this is equal to the integration from 0 to 2 pi, integration from 0 to pi over 4. Now I'm integrating with respect to rho only. What's the integration rho square? It's rho cube over 3 sine phi. We don't touch the sign, it's constant here. And this is from 0 to 3. And then d phi d theta. And this is equal to the integration from 0 to 2 pi. Integration from 0 to pi over 4. Now we're going to replace phi with 3. So it's 27 divided by 3, which is equal to 9. Then we plug the 0, you get 0. So it's 9 sine phi. Done with this one. Then we say d phi d theta. Now this is equal to integration from 0 to 2 pi. What's the integration of sine? It's minus cosine. So this is minus 9 cosine phi from 0 to pi over 4. And then d theta, which is equal to negative 9 goes out, integration from 0 to 2 pi. Put the pi over 4. What's cosine pi over 4? It's 1 over root 2. Minus. What's cosine 0? It's 1. And then d theta. Take all of this out. I'm going to put it here. So the answer is negative 9. 1 over root 2 minus 1 all goes out. What am I left with? 0 to 2 pi of d theta, which is going to be negative 9. 1 over root 2 minus 1. The integration of d theta is theta from 0 to 2 pi. So the plug 2 pi minus 0, which is 2 pi. So the answer is going to be minus 18 pi, then 1 over root 2 minus 1. This is the final answer for the volume of this one. All right, let's go to the last question. We have 3 things to graph here. Use spherical coordinates to find the volume of solid bounded by, you know, this one. This is a sphere of radius 2. So let's make the graph. So a sphere of radius 2. And then we have this goes like that. In the back goes like this. And here it goes like that and continues all the way down. But we don't care. Now this one in the back goes like this and goes all the way down. Yeah. So this is the sphere of radius 2. Then who's going to come now? Y equal to x, guys. Y equal to x. Y equal to x probably is going to be the line that comes like this. Let me put it in another color. It's pointed out. Y equal to x is exactly maybe this, something like this. This is y equal x. Of course, it goes also to the back. But y equal x is what? Is a plane, guys. Y equal, if I extend this one a little bit, what's y equal x, by the way? If you can imagine that, it's a plane. So when the plane cuts, what's the result? The result is exactly here. It's that thing, you see? The result is going to be something like this. This is the result of the cut of the sphere. Also, y equal root 3x I'm going to make it in green. Root 3x is this one now. This is y equal root 3x. And this one is going to go all the way up. This is another plane, by the way. And this is the result of the cut. So the result of the cut, guys, is exactly that shape. You see? That's the shape that we are talking about. Only this one here. So the red one here. So this is the shape that we are talking about. You want to put it all in green, we can do that. I'm trying to show you exactly where is my shape. This is the shape that we end up with. See, that's only that piece. It's like a slice. I got a piece of cake from that one whole, sphere. Z equal to 0. What's Z equal to XY plane? So this is supposed to continue down, but I'm not going to go all the way down. Why is that? Because I'm going to come to Z equal to 0 and cut it. So this is our base. This is the base now, right? So this one is Z equal to 0. Cut it at the bottom on the XY plane. This is the Y, and this is the X plane. Interesting shape. So this is the result of the cut. Now we need to find the volume. What's the volume equal to? Triple integration uses spherical. So what do we say? Rho square sine phi, then d rho, d phi, and d theta. All right. Now, what do we know about rho, guys? Let's take rho to be this line. I'm going to now show you where rho can be. You can start from 0 all the way to what? To the skin of the sphere, but inside your region. What's rho here, guys? This is a sphere of radius what? Radius 2. Then I know that rho is 2. So my rho here is going to start from 0 to 2. That's very easy. Okay, now, look, to be inside, rho is going to start from where? From the positive. Now, let's talk about phi, guys. Phi. Phi is the angle between the positive z-axis, which is 0. Now we're talking about phi. Up to what? You see, to be inside, you're going to start from here. Then you're going to come here. Then you're going to come here. Then you're going to come here, definitely. Then you're going to continue here. Then finally, you're going to lay down here, right? This is the last thing. So to continue in that pattern here, okay, you start from 0 all the way to what? What's the maximum? Definitely, it's what? Pi over 2, isn't it? You can't go beyond that because you have to stop on the XY plane. So the angle between Z and the XY plane is what? Is 90 degrees. So it has to be up to pi over 2 only. All right. So now this is what we have for the value of phi. Okay. You can find it also in another way. How do I find phi? We know that Z or phi, okay, well, Z equal rho cosine phi. But Z here, when you reach all the way down, what's this Z? It's 0 equal to rho is given to be 2 cosine phi. So divide by 2, so cosine phi is equal to 0. We know that cosine is equal to 0 at what? When phi is equal to pi over 2. So here we know that Z is equal to 0. I applied it to this and I know already, so I got pi over 4. And here it's definitely 0. The start is always 0 up to pi over 4. Now, what do we need to know also, guys? We need to find at y equal x here. Now, let's find theta. You have 2 lines, okay? Here is theta. Let's talk about the first theta. So let's choose the brown one. Here is theta 1. Theta 1 is the angle between what? The x-axis and y equal x, isn't it? It's the theta is the angle between the positive x-axis and y equal x. This is y equal x, isn't it? That's the first line. How do we find that one? Here we know, when you are there, we know that z is equal to what? 0, right? When you're on the xy plane, we know that z is equal to 0 and y is equal x. So what do we have, by the way? We have x squared plus y squared plus z squared is equal to what? What's the equation of that? It's equal to 4, isn't it? You are in the sphere now. Now, z is 0, y is x, so we have what? 2x squared is equal to 4. So x squared is equal to 2. So x is plus minus square root of 2. I don't want the negative, I need the positive only because x is distance. So I'm going to take x to be square root of 2. Now, what do we know about x? X is equal rho sine, I believe. X is equal rho sine phi cosine theta. We know that rho is 2. Phi, we already found it. When you are there, what's phi equal to? So this is sine. Phi is 90, right? When you are on the ground, on the z, phi is 90, we know. And cosine theta. What's theta when you are there? This is what we need to find, right? So we say cosine theta. And this is equal to what? X. What's x? It's root 2. So root 2 is equal to, now what's sine 90? Sine 90 is 1. So this is cosine theta. So cosine theta is root 2 over 2. This implies that theta is what? Pi over 4. So when it comes to theta, we're going to start from pi over 4. Up to what, guys? You're going to continue now to this one, to the second part, right? For the second part now, what do we know about y here? Same trick, guys. We're going to apply the same trick. So what do we, I'm going to do it here. We know that x is equal rho sine phi cosine theta. But here, x is what? So let's do the same thing here. Now we know x squared plus y squared plus z squared is equal to 4. We know at the on the ground z is 0. And we know that y is what? Y is root 3x. So square it, you get 3x squared is equal to 4. So that means 4x squared is equal to 4. So x squared is equal to 1. So x is equal to 1. So what we're going to do here, now we're going to go to this one. And we say 1 is equal rho, which is 2, sine phi, which is 1, cosine theta. So cosine theta is equal to half. When is cosine theta is equal to half? When this is equal to pi over 3. Right? Is it pi over 3? I think it is pi over 3. That's correct. So this theta 2, so we can say theta 2 is pi over 3. So up to pi over 3. This is the second theta, guys. So theta is going to start from 0. The first one, you are here. How far is the first one? It's pi over 4. Then, so to be inside, you have to go from here to here. Right? This distance. So from pi over 4 to pi over 3. And then you start the integration as usual from inside d rho. Same thing, you get rho cube over 3 and finish all of that. And you will get from this one that the answer is, I have the solution on that part, 2 pi over 9. So try it, guys. So if you want, we can take this one to the other level. So this is equal to the integration of pi over 4 to pi over 3. And this is from 0 to pi over 2 for the rho. Then the integration of rho square is rho cube over 3 sine phi. And we know that rho is from 0 to 2. then d phi d theta. Put the 2. So this is the integration from pi over 4 to pi over 3. Integration from 0 to pi over 2. Put the 2 for this, you get 8 over 3. Take it out. And I'm left with sine phi d phi d theta. The integration of sine phi is negative cosine phi. So you get minus 8 over 3 integration from pi over 4 to pi over 3 integration. Sorry, I'm going to integrate this one. The integration of sine phi is minus cosine phi. Here is cosine phi, and the minus is outside from 0 to pi over 2. Then d theta. And this is minus 8 over 3 integration from pi over 4 to pi over 3. Now, we plug pi over 2 for phi. Cosine 90 is 0, guys. Minus, put the 0. Cosine 0 is 1. D theta. The minus goes out. You get 8 over 3. Integration from pi over 4 to pi over 3 of d theta. And this is 8 over 3. What's the integration of d theta? It's theta from pi over 4 to pi over 3. And this is 8 over 3. You put pi over 3 first, then pi over 4 next. And this is 8 over 3. The least common between those is 12. 12 divided by 3 is 4. So you get 4 pi. 12 divided by 4 is a 3 pi. And this is 8 over 3 times pi over 12. This one is 4. This one is 6. So you get 4 pi over 18, which is actually equal to, I don't know why did I make this one 4. So this is divided by 4, you get 2. By 4, you get 3. So 2 pi over 9, and we remove that one. Okay, this is the final answer, guys. That's it. This is what you get for the graph of that one. And this is the volume of this solid. You see that piece, the green piece? This is how you do it. And thank you guys for watching this. It's been a long journey here. Today is a long session. So hopefully you understand it. Repeat this one more than once, you get the idea. You guys have a good night and see you in the next video. Bye-bye.